All right, the last rule that we're going to talk about is Pauli's exclusion principle. This states that each electron must have its own unique set of quantum numbers. All right, so as a result of Pauli's exclusion principle, electrons in the same orbital orientation at the same energy level must have opposite spins. So when we go to double up in an orientation, the first electron will be an up spin. When we double up, that second electron has to have the opposite spin, so it will be a down spin. This would result in the same energy level, the same orbital shape, the same orientation, but a different spin. And by having that different spin number, it is a unique set of 4 quantum numbers. And that's what Pauli's exclusion principle states. And as a result, 2 electrons in the same orientation have opposite spins. So let's see this in action. Here's our 2p orbital again, 3 orientations. If we look at this red circled electron, we can assign quantum numbers to this electron. So the quantum numbers for this red electron, it has an n of 2 because it's the second energy level. We know that because it's a 2p. The L, the shape of the orbital, is p. And when you're a p orbital, your L is always assigned a value of 1. Your M sub L, which is the orientation, and remember with 3 orientations, we have a -1, a 0, and a +1 orientation. The middle dash is always 0. To the left is going to be -1. To the right is going to be +1. So because we're in the first orientation, our M sub L is going to be a -1. And then our M sub S, the spin, is an up spin, so we assign it a +1/2. This is compared to this green electron. The quantum numbers for the green electron, the energy level is still the same energy level, still 2. We're still in a p orbital, so the L quantum number is still a number 1. We're still in the first orientation, so the M sub L is still a -1. But now we are a down spin, so the spin number is now -1/2 instead of +1/2. So each of these electrons has its own unique set of 4 quantum numbers because the spin numbers are opposite. And that is Pauli's exclusion principle. All right, if we put this all together, we're going to look at drawing some orbital diagrams and writing electron configurations. So first of all, let's draw our orbital diagram before we put some electrons in, which we use arrows to show these electrons. So let's put them in the order of Aufbau's principle. So we have a 1s, a 2s, a 2p, and convince yourself that you need 3 dashes to represent each of the orientations for our 2p orbital. And then we have 3s, and finally 3p. What we're going to do is we're going to place electrons for each of the elements. So hydrogen has only 1 electron. That first electron is going to go in the 1s orbital with an up spin. So hydrogen has a configuration of 1s1 because there's 1 electron in the 1s orbital. When we move on to helium, helium has an additional electron. That additional electron is going to be paired in the 1s orbital with an opposite spin according to Pauli's exclusion principle. And so now we have 2 electrons in the 1s orbital. So the electron configuration for helium is 1s2. At this point, our first energy level is full. And if you look at the periodic table, we just found our way to the noble gases at the end of period 1. So the first energy level is full at the end of period 1 with helium. We then have lithium. Lithium's third electron is going to have to be placed in the 2s orbital with an up spin. So now lithium has 2 electrons in the 1s orbital and 1 electron in the 2s orbital. So its electron configuration is 1s2, 2s1. Beryllium, 4th electron, will need to be paired in the 2s orbital with a down spin. So the electron configuration for beryllium, showing the 4 electrons that beryllium has, will be a 1s2, 2s2. Boron, 5th electron, has to go in the first orientation of the 2p orbital with an up spin. So boron's configuration, 1s2, 2s2, 2p1. Now carbon's, 6 electron. According to Hund's rule, where will the next electron in the 2p orbital go? I hope that you said that it would go in the next orientation by itself with an up spin. This is the movie theater rule. We're going to give each electron its own orientation until we have to double up. So now carbon's electron configuration is 1s2, 2s2, 2p2. Nitrogen's, 7th electron. Where is it going to go? According to Hund's rule, it's going to have its own, it's going to be in the 3rd orientation by itself with an up spin. Nitrogen's electron configuration, 1s2, 2s2, 2p3, because there are 3 electrons in the 2p orbital. All right, now when we get to oxygen, this 8th electron, do you see that it now has to pair up in the 2p orbital? But it's going to have an opposite spin, according to both Hund's rule and Pauli's exclusion principle. Configuration, the electron configuration for oxygen, 1s2, 2s2, 2p4. Fluorine, the 9th electron, will have to pair up in the middle orientation of the 2p orbital. Its configuration, 1s2, 2s2, 2p5. And then finally, neon, the 10th electron, will pair up in the final orientation of the 2p orbital. The configuration for neon, 1s2, 2s2, 2p6. Now at this point, do you see that the second energy level is now full? And if we look on the periodic table, we have now come to the end of period 2. We've come to neon, which is the second noble gas. All right, sodium. The 11th electron, where is it going to go? Up spin in the 3s orbital. So the configuration for sodium, 1s2, 2s2, 2p6, 3s1. Now we've only placed 11 electrons. Remember that we have elements with hundreds, well, at least 100 electrons. And so this can get very tedious very fast. Do you see with sodium's electron configuration in red that part of the configuration is exactly the same as neon's configuration? So we can write a shorthand configuration for any element by putting the noble gas core in brackets and then putting any electrons outside that core written just with normal electron configuration. So when we talk about shorthand configurations, they're also known as noble gas configurations. You place the previous noble gas in brackets. So when I put neon in brackets for sodium, I am representing the first 10 electrons of sodium. The 1s2, 2s2, 2p6 is being represented by neon in brackets. This represents our core electrons. We write all other electrons outside of that noble gas core as regular electron configurations. So sodium has 1 additional electron the 11th electron, which is found in the 3s1 orbital. Now, when you do shorthand configurations, the only elements you can place in the brackets are the noble gases. That is it. All other electrons outside of the noble gases have to be written with regular electron configurations. All right, so hopefully you're starting to see a pattern. To help you process through this, you do have some homework to do. This should be finished before class tomorrow. Continue working through the electron hotel packet. If you hit a roadblock yesterday with that, look at it again tonight, because our conversation today may help you work through that electron hotel packet. Then you should have picked up an electron configuration packet. The only parts that are going to be assigned are on the front page. So you have the background, which is some processing questions over the rules that we talked about. And then I want you to do part 1. And with part 1, you're going to fill out a blank periodic table. So you should have also picked up a blank periodic table. And in each element box, you're only going to write the end of each configuration. So for example, in red, this is what you're putting in each box. So hydrogen's box on the periodic table would be 1s1. Helium's would be 1s2. Lithium would be 2s1. Beryllium would be 2s2. Boron would be 2p1. Carbon would be 2p2. Nitrogen, 2p3. Oxygen, 2p4. Fluorine, 2p5. Neon, 2p6. And then sodium would be 3s1. What's going to start to happen is you're going to start to see that there are certain regions on the periodic table where all of your S electrons are found, where all of your P electrons are found, where all of your D electrons are found. As you're filling out your blank periodic table, make sure that you have that green Aufbau principle shortcut so that you know the order in which you are filling these electrons. A hint to you, when you get to the transition metals, count the number of electrons or count the number of elements in one period of the transition metals. There are 10 elements in one period. That is not a coincidence. Which orbital can, with 5 orientations, can accommodate 10 electrons? That's the d orbital. So all of our d electrons are found in the transition metals. Right? This blank periodic table should be filled out and completed before you come to class tomorrow, because this is where we're going to start our discussion. All right, and keep working through all of this material, as there is a 100-point quiz on Friday. All right, any extra time left in class, you can go ahead and start working on your homework.